And another session now on modeling the this one and, well, not so much the next one. This one we're going to be talking about harmonic motion. Let's just check where we are. Done. Really done. We did a lot with this, didn't we? We also did a lot with this. And starting with the session before this, we started working on creating trig models. We're going to continue this today. We're going to go through a couple examples here. These are right out of your workbook. Sinusoidal curves. Anytime you have periodic data, whether it's temperature data, electric currents, musical tones, radio waves, sunrise, the position of the sun, you're going to see sinusoidal curves. So these are very important in the world around us. We're going to take a utterly contrived idea here, and this is Tarzan swinging back and forth on his grapevine. And as he swings, he goes over the riverbank, and then back over the land, and over the river, over the bank. So Jane, his faithful companion here, decides to mathematically model his motion. So who's the mathematician here? Isn't that nice? Let t be the number of seconds the stopwatch reads. This is going to be our input, isn't it? This is our input variable. And y, that's our output. The number of meters Tarzan is from the riverbank. Assume that y varies sinusoidally with t, and that y is positive when he's over water. So when he goes over water, positive, and when he's over land, here's a riverbank right here, it's negative. Jane finds that at 2 seconds, Tarzan is at one end of his swing, and he's 23 feet from the riverbank over land. So we said that would be right here, right? That's at 2 seconds, he's 23 feet from the riverbank. At 5 seconds, he's out over the water. We said it was positive when he's over the water. So at this end here, at 5 seconds, there's our input always first, and our output is distance from the riverbank. 17. Generate the equation that represents his swing model. We're going to find the 5 points for sinusoidal. This is harmonic motion here. Back and forth, back and forth. A pendulum would be an example of harmonic motion. A spring that's oscillating up and down would be an example of harmonic motion. We're going to use techniques we've already worked with. Let's see. We know that one end of this is 5 and 17, and another end is 2 and 23. But I guess we'd say this one's a negative, wouldn't we? Yeah, because we agreed that the position is positive over water. So this is positive, and this one's actually going to be registered as negative. I'm going to pick this up on the next. So I've got 2 seconds. Well, let me go back here. I shouldn't. I should change these positions, shouldn't I? We usually put the smaller input variable over here and the larger one over here. So let me do it correctly here. Erase that. I'm going to say this is, when this is 2, he's over land, which we have agreed is going to be negative direction. At the riverbank, it would be 0. And at 5 seconds, he's at the other end of his swing. At 5 seconds, he's at the other end of his swing. A peak or a valley. I'll just leave it like I've got it right now. See what I can do with it. So I'm going to select cosine because what I'm seeing I have is a negative 23 here, a positive 17 here, and we're going to have to, would come back to negative 23 to end the cycle. And somewhere in between I've got my central axis. So I'm thinking I've got something that looks like this, which would be cosine, and it would be reflected, wouldn't it? Because ordinarily cosine starts high and goes low. Use the axis of the curve to determine d. Well, the axis, if this is a negative 23, and this is a positive 17, 40, isn't it? The difference between those, or the difference from here to here, is 40. So midway between them, take 17 minus 23, we're going to add a negative basically, and take the difference between them. I'm going to add them together and take the difference. Let's see. So on 17 minus adding a negative and divide by 2. Does that seem right? Negative 3. Okay, let's look at it and see if it makes sense to us. If this is negative 3, then from here to here is 20, and from here, negative 3 to a positive 17 is also 20. So I've got an A, which is 20. It's reflected, so I'm going to use a negative. The axis of this curve, my D, it's shifted away from 0 downward to negative 3. What's my period? Okay, so if it's sinusoidal and this is the low point, I'm coming back to the low point over here. Whoop. And when is that going to happen? Well, it was 3 seconds to get to the high point. It's going to be another 3 seconds, so this would be 8. So my period is 6. So to figure out what my frequency is, it's going to be 2 pi divided by the period I have of 6, and we should pay attention here. This would be in radians, right? So that's pi over 3. Do we have a phase shift here? Well, yes, we do. We have a phase shift of positive 2. So what does our equation look like? We've got all the parameters, we can put the equation together. We've got y equals, we do have a vertical shift of -3, and then it's going to be a reflected value, so negative the amplitude of 20 cosine pi over 3, and then we've got our time in seconds minus a positive phase shift of 2. All right, very good. I'm going to grab this equation and copy it over to the next page. Maybe we'll make it a little bit smaller, and I'll put it right here for reference. The other thing I think might be handy for reference is what we learned here about how we're varying. Y is positive when Tarzan's over water and negative when he's over land. So I'm going to grab this, copy, and we're going to just make a little diagram here. I'm going to, okay. So there's the riverbank. This will just help us out a little bit. I'm going to put in some blue water to remind us that when he's over the river, we've got a positive. And I'm going to put in some green grass to remind us that when he's over land, it's negative. Okay? So, where was Tarzan when Jane started her stopwatch? When she started, that would be at t equals 0, wouldn't it? Okay, I have already set up the window here. At least I think I have. The window. Going from 0 to 8, the cycle was actually from 2 to 8, but going from 0 to 8 with a scaling factor of 1, y min, I went one more than the 23 to a negative 24, y max 18, and a scaling factor of 3. Then let's put in the, I've already got it there, negative 3, that's the translation up and down. It's reflected, so it's negative 20 cosine, pi over 3 for our frequency, and we're not using t, but we know it represents t, x minus 2. So let's see what that graph looks like. Nice sinusoidal. Where was Tarzan when Jane started her stopwatch? Well, we could trace that back to 0, and what do we see? At that point, it was a positive 7. So when she started her stopwatch, y equaled 7. So he was 7 feet over water from the riverbank. Find the smallest value for t when Tarzan was directly over the riverbank. That would be right here. That would be 0. That's y equals 0. Let's use our trace function again. Where is it that y, that's pretty close, 0.326. We're looking for y being equal to 0. Well, we're pretty close, but if we want to get exact, I'll show you what we can do. Second function, calculate, that's on trace, and we want to find the 0 for this function. That is, where does y equal 0? Left bound, we've already got our tracer on left bound. We'll hit enter. And then we'll go to right bound. Just have to move the tracer beyond the 0 on the right side. So we've got that. And then it says guess. I say yes by hitting enter. And it gives me a value of point for when y equals 0, a time of 0.356 seconds. That's the smallest t value. Now we keep swinging back and forth over the riverbank, but so at t equals 0.36 seconds. How long is Tarzan over water? Now I should actually say, I think, in one cycle. So I think we should start not here, but over here, and oops, I need to be in trace. So where is he over water? That's all the time that he is positive, right? The distance is positive. So approximately, this is pretty close to when he first is over water, and that's at 3.6 seconds. And he stays out there in positive land over water until right about there, 6.4 seconds. So 6.4 minus 3.6, it's 2.8 seconds over water in each cycle. Finally, where will Tarzan be 1 minute from the time Jane started the stopwatch? 1 minute equals 60 seconds. So let's use our calculator on this. We would, okay, clear this. Minus 3 minus 20 cosine of pi over 3 times 60 minus 2, which would be 58, gives us an answer of 7. So he'll be 7 feet from the riverbank. Which is the very same place he was at, and that's over water, at t equals 0 over water. I should say that. It's important, isn't it? Harmonic motion. Here's another example. Mark Twain sat on the deck of a river steamboat. This is true, isn't it? As the paddle wheel turned, a brightly painted yellow dot on the paddle blade moved in such a way, now this isn't actually true, but if there had been a brightly painted yellow dot, it would move in such a way that its distance from the water's surface, right, it's going to go like this, right? So its distance from the water surface is getting closer and closer to the water surface. It goes negative underwater, then comes back to the water surface, goes positive, positive to a maximum height, comes back down, goes to 0, then to a minimum. So we've got a sinusoidal function of time. Our input is time. When the watch read 4 seconds, the dot was at its highest point, which would be right here. That makes perfect sense. So that's a point of 4 and 16. Whoop. And then we have another point down here, which is something, and the wheel's diameter is 18 feet, so that would have to be a -2, wouldn't it? It'd be just 2 feet underwater. It completes a revolution every 10 seconds, so it's going to be back up to 16 feet above the water, its maximum, 10 seconds later, so that would be at 14 seconds. Midway through this cycle will be how many seconds? 9, right? And at that point, going from here halfway, time-wise, is 9. And where are we with distance? We're at -2. Generate an equation for the sinusoidal curve. All right. So if I think about this, at 4 seconds, y is 16. At 9 seconds, y is -2. And at 14 seconds, y is 16 again. So got something looking like this. So I think we'll call this cosine, right? And is it reflected? No, it's not. Use the axis of the curve to determine d. Well, that would be midway between 16 above and 2 under. The total distance here we know is 18 feet. Half of 18 is 9. So if I go 9 below 16, I'm at, and 9 above -2, I'm at 7. Okay, so this is equal to 7, and it's positive. The height of the curve above its axis, so this is saying y is 7 at the midpoint. Let's check this out. So 16, 7, -2, 7, 16, a full rotation. Or looking at it over here, 16, 7, -2, 7, 16. The height of the curve above its axis is 9, and it's not reflected, so it's going to be positive. What is our period? It's 10, so that's going to be pi over 5, isn't it? 2 pi over 10, pi over 5. Phase shift, yes we do. We have a positive phase shift of 4. So C is equal to 4. So here's our equation. Y equals a positive 7 plus, we've got an amplitude of 9. We're using cosine with a frequency of pi over 5. And we've got t minus a positive. How far above the surface was the dot when Mark's stopwatch read 5 seconds? Well, let's pull out a calculator here, adjust our window. Let's still go from 0, and our max is now going to be 14. We'll leave our scale at 1. Our minimum is, for our y, is going to be -2. Our maximum is going to be 16. And why don't we do a scale of 1? Now we'll put our equation in, clear this old one out. We've got 7 plus amplitude of 9 times cosine pi divided by 5 times, now we have parentheses, we're going to use again x as our variable for time, minus 4. And now we'll graph that. Alright, so we can see what it looks like. How far above the surface was the dot when Mark's stopwatch read 5 seconds? Okay, let's turn on our trace and see if we can get there. So we're looking for x equal to 5. Let's do x equals to 5. We can just put it in and see what happens. It says 14.28. Okay, so the answer to this first question, 14.28, and we're talking here feet. How long was the dot below the water's surface? Basically, we're asking, oh, something's wrong with my window. I better fix this window because I can't really see, probably because I'm tracing and this is writing over my trace. So let me adjust the window just a little bit. We'll go down to -4. See if, okay, now maybe when I trace I'll still be able to see where I am. Yes. How long was the dot below the water surface? So we're going to trace that to do an estimate. We could do exact. That's pretty close, isn't it? So 7.89 when it first goes underwater. This is in just one cycle. And now what time is it when it gets back to the surface? 10.1. So we're going to say 10.1 minus 7.9. 10.1 minus 7.9. So our answer is 2.2 seconds underwater. From the time when the stopwatch was started, when was the first time that the dot was at the surface of the water? So the dot is at the surface of the water when y equals 0, isn't it? Because that's what y is representing, how far the dot is away from the surface. So at 0, it's right at the surface. From the time when the stopwatch was started, so I'm going to use, I'm going to use my trace mechanism here, and we're going to go back to the start, let me look at my window. That's 0, right? So at the very beginning, when t is 0, it's underwater. So it was underwater. From the time when the stopwatch was started was the first time that the dot was at the surface. So when it starts, it's under, just slightly. And then at, well, should I go for the exact? I probably should. Okay, so I'll go for the exact. We'll say calculate, second function calculate, I want to find the 0. This is when it is right at the surface. Left bound, I have left bound. Now let's do right bound. I need to go beyond the 0. Guess, yes, please guess. That was at 0.08 seconds. Wasn't even 1 second yet. So at 0.08 seconds, it was emerging from the water. Here's another example of harmonic motion. Add a mass oscillating up and down on the bottom of a spring. Here it is, the weight. And right here you see it being displaced downward, right? The 0 position is right here, and then when it is contracted, it's up here. So we've got perfect elasticity, no friction or air resistance. Is that real? No. So we're looking at a perfectly oscillating body, nothing getting in the way of this harmonic motion. At least it tells us theoretically, huh? If the weight is displaced at a maximum of 5 centimeters, find the modeling equation if it takes 2 seconds to complete one cycle. So what will one cycle look like? It'll look like going from 5 centimeters down to -5 and back up to 5 again, right? And here's 0 in the center. So we've got 0, we've got 5, and we've got -5. Find the modeling equation if it takes 2 seconds to complete one cycle. So that's our period. So what is our B then? 2 pi divided by 2, or pi, right? If the weight is displaced at a maximum of 5 centimeters, we know our amplitude is equal to 5. What about D, our central axis? That's actually 0, isn't it? D equals 0. What's the other thing we have to think about? Whether or not we've got a phase shift. And the way we're defining it here, starting at 5, there's no phase shift. So C is equal to 0. Oh, this is the easy one. I love this one. And we're going to use cosine, right? This is the cosine. So y equals, we have no vertical translation. Our A is a +5. This is not reflected. This is normal. So we say 5 cosine and we're going to say pi x. No, in this case t. In fact, let me choose the correct. All right, I'll do it all over again. Because we were going to use d for distance. D equals 5 cosine pi t. That would be our equation. Find the displacement at 1.25 seconds. I would just put 1.25 in here and see what I get for an answer. Is the weight moving up, down, or neither at 1.25 seconds? Well, this is where looking at the graph really helps a lot. So let's turn this on. We'll change our window again. We'll have a minimum of 0. What are we looking at for time? We're looking at 2 seconds. So 2, we've gotten through the full cycle. We'll have a scaling factor of 0.5. For our displacement, we're going to be going from -5 to +5. So -5 to +5, and we'll leave the scaling factor at 1. Let's put our new equation in here. It's 5 cosine of pi. I'm going to use x, of course, but we know it stands for t. Okay, and we'll graph this. So now, with the graph in front of me, find the displacement at 1.25 seconds. Okay, so if I put in 1, back to my graph. Let's go for x. That's not going to work. Okay, let me put it into trace. And I'll put in 1.25. And that tells me at that point it is -3.53, but I can see on my graph, is it moving up or down? It's moving up. It's moving up. Find the displacement. It's -3.53, -3.5, actually 4 when we round it, and that's centimeters, and it's moving up. Okay. Okay, we'll see you back in class.